The first part of the stud wants you to consider concentration in the overall mixture such that Z is equal to 0.65. It asks you to calculate firstly the pressure range where a two-phase mixture can be observed. This of course means that it wants to know what is the bubble point and the dew point pressure at this specific overall composition of the mixture. So a different way of asking this question would simply be calculate the bubble point and the dew point at this concentration. Both procedures are well explained in example 10.3 in Smith, Van Ness and Abbott. Part A for a simple bubble point calculation and part B for a dew point calculation. Basically, it requires the solution of two simultaneous equations, either equation 1 for the sum of the pressures must be equal to the total partial pressures must be equal to the total pressure, or sum of the mole fractions in the liquid phase must be equal to 1. That will be equation 1, and the second equation is of course the modified Rolle's law. The dew point calculation is the most tricky of the two, since the unknowns in this case is x and the pressure, which means that we cannot calculate the activity coefficient before the start of solution of the problem. And that is if we do a hand calculation, which you would typically have to do in a test or an exam situation. So a trial and error or a fixed point iteration procedure will be required. To start your loop, therefore set gammas equal to 1. Then next step would be to apply equation 1b in order to solve for the pressure. Once you have this first guess value for your pressure, you can apply equation 2 in order to solve for your x values. Once you know the x values, the activity coefficient equations can be applied to calculate new gamma values. This can then be used in equation 1b again to calculate a new pressure. Your system or your trial or your loop would be exited once the pressures reach convergence. The second part of the question still wants you to consider an overall mole fraction of 0.65, but in this case they want to know what the vapor fraction would be at that pressure where the liquid phase mole fraction is 0.75. So in other words, it's going to split into a vapor fraction with this composition, a liquid fraction with this composition, and how much will be in the liquid phase. So for this, we are going to apply a mole balance. So if we choose an arbitrary mole fraction or a total mixture, we know that it will split into a vapor phase number of moles and a liquid phase number of moles. A mole balance on component 1 says this 0.65 of this total number of moles must split into whatever is in the vapor phase plus whatever is in the liquid phase. So of course now we know this value. We can choose that as balance, choose a basis of 1. We know this mole fraction needs to be 0.75. So we have 1, 2, 3 additional unknowns in this equation. One equation, we've got our second equation. In order to determine that mole fraction, we are going to apply a Rolle's law. And now we see that we build in yet another unknown, which is that pressure at that point where that phase will split, but we are not worried because we can apply the sum of mole fractions, or the sum of the partial pressure, must be equal to the total pressure. Right, so since we know our x's, we can calculate the gammas, we know our temperature, we can determine the pressure where that will be true. Once we know the pressure, we can apply that to solve the mole fraction in the vapor phase. Once we know the mole fraction in the vapor phase, we can substitute that into our mole balance for component 1, and we can set, if this is a basis equal to 1, we can substitute the liquid phase fraction as a function of the vapor phase fraction. And it's then easy to solve how much of your mixture will split, or what fraction of the mixture will be in the vapor phase. Of course, the easiest test for the existence of an azeotrope is to determine the relative volatilities where x1 goes to 0 and of component 1 versus 2 where x1 goes to 1. In this case, if we calculate them, and I'm showing them here as a function of the mole fraction, we can see that this magical limit, alpha 1, where the azeotrope does exist, in our case for this system is never reached, because at the two endpoints we have two values for the relative volatility that's less than 1. So no azeotrope.